A vector subspace is a non-empty subset of a vector space that is closed under the same addition and scalar multiplication as the vector space. In this video, we'll show that a vector space must contain the zero vector, and the vector subspace itself is a vector space. And we'll give a few examples, including the set of solutions for a homogeneous linear system is a vector subspace. Okay, let's start. So here's the definition. Let V be a vector space over a field F, and let W be a non-empty subset of V. So W is non-empty and W is a subset of V. Then W is said to be a vector subspace, or simply a subspace of V, if these two conditions are satisfied. First, if U and V belong to the subset W, then their sum, U plus V, also belongs to the subset W. And second, if V belongs to W and C belongs to the field F, then the scalar multiplication C times V also belongs to the subset W. Of course, this addition and this scalar multiplication, they are as defined in the vector space V. From this simple definition, many practical applications, useful practical applications can follow. But before that, we prove some basic properties of vector subspaces. The first property is this. If W is a subspace of V, V is a vector space, then the zero vector belongs to the subspace. The proof is quite simple. Since W is a subspace, then it is non-empty by definition of a subspace. So we can choose some element from W, let's say V, element V. And let's pick the zero element of the field F, since we're assuming this vector space is a vector space over the field F. Then 0 times this V belongs to the subspace, according to the definition of the subspace. But 0 times any vector is a zero vector. So that means zero vector belongs to this subspace W. And we are done. So some people prefer to use this fact as part of the definition of subspaces. So instead of saying W is a non-empty subset of V, we can say the zero vector belongs to the subset W. It's almost the same thing. Here are examples of trivial subspaces. Let V be a vector space over a field F, then this singleton set that contains only one element, that is the zero vector, is a subspace of V. In fact, the only element is the zero vector, so 0 plus 0, which is the 0, belongs to the subspace. And C times zero vector, where C is any element of the field F, is a zero vector, so that belongs to the subspace. So this W is a subspace. And another trivial subspace is the set V itself. So it is a vector space already. So it is closed under addition and scalar multiplication. So it is a subspace of V itself. Next, here are examples of subset of a vector space that are not subspaces. Consider R2, which is a two-dimensional vector space over the set of real numbers R consisting of column vectors. So this is a subset of R2. So 1, 0, and 0, 1. This is not a subspace because it does not contain the zero vector. According to our theorem we proved before, the zero vector must exist in a subspace. Although this is a subset, it's not a subspace. So what happens if we add the zero vector in addition to these vectors? So we have 0, 0, 1, 0, and 0, 1. So is this a subspace? This is a subset of R2, but it is still not a subspace because if we add, for example, these two elements, 1, 0 and 0, 1, we get 1, 1. This vector does not belong to this subset W. So it's not closed under addition. Therefore, this W is not a subspace. Next, we prove this theorem. The two conditions in the definition of a subspace, that is closed under addition and closed under scalar multiplication, those two conditions are equivalent to this one condition. That is, if A and B belong to the field F and U and V belong to the subset W, then AU plus BV belongs to the subset W. So we can summarize the two conditions in the definition in this one single condition. Okay, let's prove it. Since we are trying to prove the equivalence between two sets of conditions, we prove one implies the other and vice versa. So first assume the definition one, the conditions in the definition one holds, and then we prove this. Okay, so since the two conditions in definition 1 holds for any AB in the field F and any UV in the subset W, the scalar multiplication is within the subset W. So AU belongs to W, BV belongs to W by condition 2. And by condition 1, their sum also belongs to the subset W. So definition 1 implies this condition, and then we prove the converse. So suppose this condition holds. So then if we put A and B equal to 1, then we have, so A times U plus B times V becomes just U plus V. That belongs to W. So W is closed under addition. And next put A equal to 0 and B equal to C. Then U times 0 times U is the 0 vector, and the 0 vector times C times V is just C times V, because adding the 0 vector doesn't change this vector. So therefore, this becomes just CV, which belongs to W. So W is closed under scalar multiplication. Therefore, the two conditions in definition and this one, they are equivalent, and we are done. So because of this theorem, if we want to prove a subset of a vector space is a subspace, then we can just check this single condition. One important aspect of a vector subspace is that it is a vector space. So let W be a subspace of a vector space V. Then with the same addition and scalar multiplication as in V, W itself is a vector space. Let's prove this. To prove some set is a vector space, we need to show that with addition and scalar multiplication, it satisfies the 10 axioms of the vector space. So that's what we will do. So the first axiom, W is closed under addition. This is trivial because this is part of the definition of a subspace. Then associativity of addition, this is trivial because this addition is the same addition as in the original vector space, so associativity always holds. And addition is commutative. This is again trivial due to the property of the vector space. And we have shown that the zero vector exists in the subspace. And if V is an element of W, then -1, which is an element of the field F, times V belongs to W according to the definition of a subspace. But -1 times any vector is the additive inverse of that vector. We have shown this in another video. Therefore, the additive inverse of any vector exists in the subspace. And next, for any scalar C and any vector V in W, then C times V belongs to W. This is part of the definition of a subspace. And the associativity of scalar multiplication is trivial because this is a property of the original vector space. Also for the distributive laws. And this one is the multiplicative identity in the field F times V is always equal to V. So this is also trivial from the properties of the vector space. Therefore, all these 10 axioms are satisfied for the subspace. Therefore, W is a vector space. And we are done. Now let's turn to non-trivial examples of vector subspaces. Consider R3, so it's a three-dimensional space. It's a vector space of three-dimensional column vectors. Then let W be defined by this. So it is a set of column vectors which satisfies this condition. So the sum of their elements x, y, z is equal to 0. So this is indeed a subset of this space. Then this W is a subspace. Let's prove this. So let U and V be elements of W. Then according to the definition of this W, U1 plus U2 plus U3 is equal to 0, and V1 plus V2 plus V3 is equal to 0. And for any AB, real numbers AB, then this linear combination, A times this vector and B times this vector is this vector, according to the vector algebra. Now, let's add these three elements. So we have this plus this plus this. But if we factorize, we have A times U1 plus U2 plus U3 plus B times V1 plus V2 plus V3. But this is 0, this is 0, because we have this. Therefore, everything becomes 0. That means this vector also belongs to this subset. Therefore, this W is a subspace. Notice that this is a homogeneous linear equation, and we can generalize this to more general homogeneous linear equations. In fact, we make it as a theorem. Let A be an M by N matrix whose elements belong to a field F. Then the set of all solutions of this homogeneous linear equations is a subspace of Fn. Fn is the n-dimensional vector space, and F is this field F, and n is the number of elements in the column vectors. So this X is a vector of n unknowns. So let's define this subset W of Fn. So it's a set of column vectors satisfying these homogeneous linear equations. So this W is a subset. And next we need to check that this W is non-empty. But the trivial solution of the homogeneous equations always exist. So 0 vector multiplied by the matrix A gives the 0 vector. So this 0 vector satisfies this equation. Therefore, this 0 vector belongs to W. By the way, this 0 vector on the left-hand side is an n-dimensional vector. This 0 vector on the right-hand side is an m-dimensional 0 vector. So don't get confused. Therefore, W is non-empty. Now check other conditions. Suppose U and V belong to W. So that means A times U is the zero vector and A times V is the zero vector. Then for any AB elements of the field F, we have this. So A times this vector, so matrix multiplication is distributive, so we can expand this like this. But this AU is the zero vector, and this AV is the zero vector. So we have A times 0 plus B times 0. But any scalar times zero vector gives the zero vector. And zero vector plus zero vector is the zero vector. That means this vector is a solution of the homogeneous linear equation. That means this belongs to W. So, therefore, W is a subspace of Fn. And we are done. Alright, that's all for this video. Thanks for watching. If you liked it, please hit the like button. And also please subscribe. I will appreciate it. Thank you very much. See you later. Bye.